So today we're going to do section 2.5, which is the delta epsilon definition of the limit. Now that is a super exciting chapter. The delta epsilon definition is the first definition that you're going to see in math as you get to this point that's different from any math you've ever seen. Because any math you've ever seen before talks about a number. 2 and 2 is 4. X is, X is something. But it's X. It's not, well, of course we're talking about X, right? What else could we be talking about if it's not a number? We are not going to talk about the number itself. We are going to talk about its neighborhood. And that's the definition of a limit. You might say, well, haven't we been through that this whole time? No, we haven't given a very precise or rigorous definition of the epsilon of the limit. And the exact definition of the limit is the delta epsilon definition. Now let's read the definition, okay? It says, let f of x be defined for all x not equal to a. That's important. It's not equal to a. Why? Because it's probably dividing by 0 at a and you don't know what to do with it. So x is not equal to a over an open interval containing a. That's also critical. That it has to be an open interval that contains a. The reason is because if it's not open, the a might be on the edge. And you cannot have a on the edge. A has to have its neighborhood, because the neighborhood that we're talking about here. Next, let L be a real number. Fine. Then, the limit of f of x as x approaches a equals to L if for every epsilon bigger than 0, there exists a delta bigger than 0 as such that if x minus a is less than delta but bigger than 0, then f of x minus L is less than epsilon. Alright, so what did I just say again? Here's what I want you to do after this video. I want you to look at this definition, which is what? About two or three sentences long, 2 or 3 short sentences, right? And this definition, and I want you to spend time, a lot of time, reading it one section at a time and keep going until you understand it. Like spend, say, up to an hour understanding this 2 or 3 sentences, because that is how the advanced math is. It's precise and it's loaded, and each word and each sentence and each comma has a specific meaning. And you got to keep it all in your head, and you read through it again and again and again until you understand it. For example, you might read the first part. Let f be defined for all x not equal to a. Okay, did you get that? All right. And then you keep going over an open interval containing a. Got that? Fine. Let L be a real number. Okay. Then, limit of f of x equal to L. And by that point, you're saying, what? Then go back to the beginning, do this again. And keep going again and again until you understand these 2 or 3 sentences. So, but in the meantime, I'm going to explain it. What delta is the variation. That is how far we're away from a. Remember, f might not even be defined at a. We are considering the neighborhood of a. And what neighborhood is that? That is the delta neighborhood. For example, let's look at a, right? A is right here. Here's your real line, okay? Here's a. And we are considering a neighborhood of a. That's has the width of delta. This thing here is delta, okay? So we are considering delta is not 0, because then if it's 0, there's no neighborhood, right? So it says delta is a small number that is bigger than 0. So here's a, which the function might or might not be defined, probably not. But that's why we're considering its neighborhood. That is, we are holding the neighbors responsible for what this thing does. Okay, we're considering the neighbors. That's why limit is such an advanced concept invented by Isaac Newton, and eventually is what we built calculus out of. Differentiation, integration, all that stuff. So, so we're considering the neighborhood, not the number, the neighborhood. What neighborhood is that? A small neighborhood. That is the numbers close to it. all of them. Every single number in this neighborhood, we're thinking about all of them at the same time. Okay, so that's your delta neighborhood. Next, let's consider L. Okay, f of x is the value of f of x over here, and L is what we're shooting for. There's another neighborhood here, the epsilon neighborhood. This distance is epsilon, okay, which is a Greek letter. Mathematicians loved Greek letters, so that's why we choose delta and epsilon. Epsilon is Greek letter E, and in English we choose epsilon because it stands for error. This is the error tolerance. What we are trying to say is, being that we cannot consider what the value of f at a is, we're considering all the value around it. Where's it going? That is, all the value around it will land through f. We're applying f here. Okay, here's f, the function. We're using f, and they have to all land within the error tolerance of L, within epsilon. That is the point. Now, if that is possible, if somebody gives you an epsilon, okay, epsilon is a small error because we don't want a big error. You allow the small error tolerance. Within the small error tolerance, if you can find a neighborhood of A such that everybody in the neighborhood that isn't A will go through F and land it within the error tolerance, within epsilon in this neighborhood, then we will say the limit exists, and the limit equals to L. And that is what this definition is talking about. Now, what happens if you find some neighborhood, okay, and most of them do land in the neighborhood epsilon, but you find a few energetic ones with ADHD. They bounce around, they land, when they go through F, they bounce outside epsilon. Then it's not acceptable, but we can see if we can find a smaller delta. It doesn't say how big delta has to be, just as long as you can find one. So let's say you found some of the exceptions. There are exceptions in the neighborhood. There are some energetic ones who will bounce out. Then let's look for a smaller neighborhood, another delta. Okay, we'll magnify out this part, another delta. We'll call it, I don't know, delta prime or something. Okay, we'll magnify it so that here's A, and here's delta prime. Sorry, I'll draw it differently. Anyway, so we'll magnify this thing. Okay, this is delta prime. There's the small area in here that I'm magnifying. Okay, a new neighborhood. And look at those instead. In other words, all the guys who jump out here, I hope. And then so you find a smaller neighborhood, you restrict it. That way you don't count the other ones, because we don't care how small delta is. As long as you can find a delta small enough that's bigger than 0, that everything in this new neighborhood can land within the epsilon that's given. The epsilon is chosen for you, and it's the error tolerance that the customer wants. Okay, they want you to build, I don't know, this chair, and it cannot be off by 1 centimeter. Okay, so that's your error tolerance. The question is, can you find a small enough neighborhood that will that everybody in this new small neighborhood will all go through F? Okay, we're going through the function. It goes through F and land in here. If the answer is yes, then the limit of A equals to L by the definition. If even in this small one, no matter how small a neighborhood you get, you always find people with ADHD that will jump out of epsilon, then the limit doesn't exist. So that's, but if you can find a small enough neighborhood where everything in this small neighborhood, okay, which used to be here, I magnified it, everything in this neighborhood going through F will land within here. It just have to land within, okay? It cannot reach the edge. As long as it's within, then the definition works. And the reason is because this applies for every epsilon. That is, the customer might give you the error as 1 centimeter, then he wants 1 millimeter, then he wants 1 nanometer. Doesn't matter how close the customer wants, you will always, if you can, always find a small enough neighborhood where everybody in that neighborhood will go within the epsilon, the error tolerance of the limit. Then the limit exists, and that's the definition of that's the meaning of the delta epsilon definition. All right, so don't forget to read through this after what I said. Don't forget to read through this carefully and spend quite a bit of time allows to read it. We'll never go through the delta epsilon definition again, but the reason I want to cover it is because it's cool. Okay, it's the first coolest. This is the coolest mathematical statement you have encountered so far if you've never had anything past calculus. It's extremely precise. I still remember the first time I read the delta epsilon definition, and it was so exciting. So all right. So your book has gives quite a big long explanation that's different from what I said. Somewhat doesn't matter how you explain it. Just just read it. Maybe read the book's explanation. Whatever. Try to read it enough so that understand it, because it's tradition. It's not going to do much, but it's tradition to understand the delta epsilon definition of calculus, because it's super cool. It's very concise, very condensed, so it takes time to understand it. But that's the whole point of studying math. You try to understand something that's dense. But anyway, as an example, let's look at example 2.39. Example 2.39 to demonstrate the delta epsilon definition. Let's look at some function called 2x plus 1. It's a quick, easy function. We're supposed to prove with the delta epsilon definition 2x plus 1 as x approach 1 equals to 3. All right, so well, you're probably thinking, haven't we done this already? Well, duh. As x approach 1, this thing will approach 3. 2 plus 1 is 3. That's just one step above 2 and 2 is 4. Or is it below? I don't know. Anyway, but in math, sometimes our goal of existence in advanced math is to prove what is obvious. So let's use the extremely dense delta epsilon definition to prove this thing. All right, so and to do that, to show how the delta epsilon definition works. So to prove it, I'm going to do a different approach than what your book says. So because I think my approach is faster, but feel free to read the book's approach too. Anyway, in the delta epsilon definition, epsilon is the error tolerance that's given to you. You have no choice. Okay, so you're given epsilon is bigger than 0. Okay, we need to do something such, by the definition, such that if x is within delta, then this thing is within epsilon, right? So given epsilon bigger than 0, you need to find that delta such that delta within 1 close when x is within delta of 1, then this thing is going to be within epsilon of 3. Now how are you going to find the delta? Here's how. You take so what you want is this. This is the function f of x. So we want the f of x 2x plus 1. Okay, now we're going to use the absolute value minus the distance of this thing from the limit has to be less than epsilon. Whatever epsilon is given to you by the customer. Okay, you have no choice about it. The customer might pick a very small epsilon, and it doesn't matter how small, you have to work with it. So that's because epsilon is your error tolerance. So you got to find some delta that will make this happen if possible. And so let's find it. So 2x minus 1 minus 3 is less than, you have to make this less than epsilon. So now we have to do absolute values. So 2x minus 4 less than epsilon. So what you need is x minus 2 sorry, I messed up here. It's 2x plus 1. So right here, plus. Why did I say minus? So this is a plus thing. So it's minus 2. Okay. Otherwise, it's like, what is going on here, right? So minus 2. So 2x minus 2 is less than epsilon, which to solve the inequality means that x minus 1 is less than epsilon over 2. Now this inequality goes backwards, which means, and we'll set this thing to be delta. Why? Because as long as x minus 1 is less than epsilon over 2, which we call delta, then this relationship holds. It will be less than epsilon like it wants. Okay? They want you to figure out some x from the distance from 1 that has to be less than that's less than a certain delta, such that the function is within epsilon of 3. See? So if you set delta equals to epsilon over 2, they'll work. So the answer is set delta equal to epsilon over 2, and then you're good. And that will be the solution.